In this video, we are going to analyze polynomial function graphs. So first, let's talk about how we determine the degree of a polynomial. Is where n is a non-negative integer. So when we're determining degree, we're going to look for that largest degree of the polynomial. So when we're talking about polynomial functions, our domain is always going to be negative infinity to infinity. The graph of a polynomial function is continuous and has smooth turns. So we don't want any sharp turns. So let's look at number 1 here, where they're going to ask us some questions. So we talk about the degree of the polynomial. That's going to come from this 4 right here, because that's the highest power of a single term. We talk about leading coefficient. That's going to come from the coefficient on the term with the highest power, so 2. X-intercepts are going to come from the graph. So if I look on the graph, I have x-intercepts at -6, -4, 0.5, and 2. So -6, -4, 1/2 or 0.5, and 2. When we're talking about a y-intercept, there should only be 1, and it's about right here. So that's going to be hard to tell. So remember the y-intercept, your x always equals 0. So if I were to plug 0 into this original equation, original function, then I would see that my y-intercept is 48. So it's always going to be that c value. Number of local extrema. All right, so when we're talking about extrema, we are talking about local mins and maxes. So if I look, I have a min, a max, and a min, so I have 3 total local extrema. The last thing they're going to talk about is end behavior. So when we're talking about end behavior, we're talking about what's happening at the ends of the graphs. So we're going to assume there's an arrow here and there's an arrow here. So this first one says what happens as the limit as x approaches positive infinity. So this is going to be what's happening on the right side. So if I look on the right side, as it's going towards positive infinity on x, it's going towards positive infinity on the y, or on the function. So my function is going to go towards infinity. If x is going towards negative infinity, this is actually the left. So the left side is negative infinity. So again, as x goes negative, my y is actually also going positive, so my function is going to go towards positive infinity. The last thing they talk about is the number of inflection points. And there's a little bit of a definition down here. An inflection point is where the function changes concavity. So if I give you like a little curve like this, for example, this would be concave up and this would be concave down. So my inflection point, there would be 1, it'd be right there. It'd be where your graph switches from concave up to concave down. So on this graph, it switches concavity about right here and about right here. So there's 2 inflection points. Let's talk a little bit more about end behavior. So this first one says the leading coefficient is positive. So again, that number is positive. So in terms of an even function, that means it'll be pointing up. In terms of an odd function, that means it'll be an increasing function. So what is happening as x goes to positive infinity? So no matter what, is my leading coefficient is positive. Both times as it goes towards positive infinity, it's going to go also towards positive infinity. So that means as x goes positive, y is going positive. So as x goes positive, y is going positive. Now, if my leading coefficient is negative, what that means is my graph would open down if it's an even function. If it's an odd degree, it's going to be a decreasing function. So then as we go towards positive infinity, my function's going towards negative infinity, and that would be true for both of these. If the degree of the polynomial is odd, then my ends will go in opposite directions, kind of like we just talked about. versus if a function is even, the ends will go in the same direction. All right, so let's use this knowledge. It says, as x goes positive, my function's going negative, and as x goes negative, my function's also going negative. What do you know about the degree of the leading coefficient, the degree and the leading coefficient of this polynomial? So it's saying as x goes positive, y is going negative, and as x goes negative, y is also going negative. So imagine my function would be like that. So I imagine that my degree would be even because my ends are going the same direction. And my leading coefficient, since my graph is pointing down, would be negative. All right, let's talk about local extrema. A polynomial has a degree of n, has at most n minus 1 turning points, or local extrema, so mins or maxes. So if a degree is even, the polynomial will have an odd number of mins and maxes. If a degree is odd, it'll have an even number of mins and maxes. When we talk about inflection points, if a degree n of a polynomial will have at most n minus 2 inflection points. So for example, if I have a polynomial of 3, what this first section is saying is that I will have 2 mins or maxes, probably one of each. If I have a polynomial of 4, I'll have 3 mins or maxes. This one's talking about inflection points. If I have power of x to the 3, that means I'll have 1 inflection point. If I had a power of x to the 4, I would have 2 inflection points. So in 3, it says a polynomial has a degree of 7. Comment on the number of local extrema and the number of inflection points. Well, if my degree is 7, that means my local extrema would be 1 less than that, so there would be 6. And my inflection point would be 2 less than my degree, so there would be 5. All right, so real zeros. So real zeros means real numbers versus imaginary numbers. So a polynomial has degree n, which means it'll have at most n zeros. So again, at most n zeros. Real zeros, because there could be imaginary zeros. These are the x-intercepts on a graph of a polynomial. If a degree is odd, the polynomial will have at least 1 x-intercept. If a polynomial is even, it will have at least none. So if it's odd, it should cross the x-axis at least once. If it's even, it may never cross the x-axis, but it could. 4 says, given the graph of the polynomial, determine the lowest possible degree, sign of the leading coefficient, and the number and location of the inflection points. So since my ends are going opposite directions, I know that my degree has to be odd. I see that I have 1, 2, 3, 4 local extrema. So that's leading me towards, if I have 4 local extrema, my degree is probably 5. Leading coefficient, well, I can see it's a decreasing function, so I know that my leading coefficient is going to be negative. Leading number of and the inflection points. So inflection point would be where the concavity changes. So 1, 2, 3. So 3. So inflection points, I have 3. So that would also support the degree of x to the 5th. So my final answer is going to be like my degree would be 5. Let's take a look at our last question on these notes, number 5. It gives us a polynomial of 5 halves x to the 5th plus 3x to the 4th minus 6x to the 3rd plus x squared minus 15. It wants to know, based on this equation, we're going to fill in some information. So first of all, this is an odd function. not degree, and it has a positive leading coefficient. So that means it's going to be an increasing function going opposite directions. So that means as x goes to the right, my function will go towards infinity, and as x goes to the left, my function will go towards negative infinity. Since the degree is 5, the number of x-intercepts, the maximum would be the same as the degree, so that would also be 5. The most inflection points, well, that's always the degree minus 2, so there'd be 3. Possible number of relative extrema, well, that's always 1 less than the degree, so potentially 4 or 2 or 0.